Welcome to the chapter in grid-connected PV systems, in which we will look at the financial and environmental aspects of PV systems. In this teaching unit, we'll take a closer look at the concept of payback period. We have now learned quite a few technical basics that we need to plan and build a PV system. This chapter will focus on another question that often arises when planning a PV system. How economical will it be? To answer this question, we can use different calculation models. In general, we can distinguish between the static and dynamic calculation methods. In the static method, it is assumed for simplification that the annual yields as well as the annual income and costs of a PV system are constant over its entire lifetime. Thus, average values are used for the calculation. This makes the static methods comparatively simple, but they deliver somewhat less accurate results. In the dynamic methods, both the yields and the income and costs for the PV system are calculated for each year of the lifetime. In addition, these methods also take into account that the value of money decreases over time. A yield of 100 euros 20 years in future generally has a much lower value than it would have today. An example of a static method is the static payback period, which we'll look at in more detail in this teaching unit. Later, we'll also look at various dynamic methods and parameters, for example, the net present value method or the cost of electricity or levelized cost of electricity. Let us first provide an overview of the expected expenses and revenues. As expenses, we first have the investment costs needed to build the system. These costs include the costs for the solar modules, the inverter, the mounting system, and all other system components. In addition, the installation of the system must also be considered, as well as the connection of the system to the grid. Furthermore, there are operating costs, for example, for insurances, rent of the electricity meter, or the cleaning of the solar modules. In addition, defects, especially of the inverter, have to be expected during the lifetime of a plant. The annual operating costs are typically set at 1.5% of the investment costs of a photovoltaic system. They also serve to build up reserves for the replacement of the inverter. Investment costs are the dominant cost component of PV systems. Shown here is the development of system costs for small to medium-sized rooftop systems in Germany. Whereas in 2006 the system price was almost 5,000 euro per kilowatt peak, in 2020 it was only about 1,100 euro per kilowatt peak. It can be seen that a large part of the cost reduction can be attributed to the lower prices for PV modules. As a result of the Corona pandemic and transport problems between Asia and the rest of the world, the module price has slightly increased again for the first time in 2020. On the benefit side, we also have various variables that are included in the profitability analysis. First of all, some states, municipalities or cities subsidize PV system with a one-time payment when the system is built. In addition, there are also various subsidy models for the feed-in of electricity from PV systems, which can essentially be divided into two categories. The first model is the so-called net metering. Here, a bidirectional meter is used to measure the electricity fed into the grid and the electricity drawn, which can run both forward and backward. This way, the electricity fed into the grid is offset against the electricity drawn. In this model, all the electricity generated is effectively subsidized with the electricity price. There are different arrangements if more electricity is fed into the grid than is consumed. In some countries, in such a case, it is possible to carry over the surplus to the next billing period. In the second model, the state ensures a guaranteed feed-in tariff for solar electricity fed into the grid. This model is followed by Germany, for example. In addition to the income from the feed-in tariff, the savings from lower electricity purchase costs due to self-consumption must also be taken into account. However, in some countries, but also for very small systems, meaning smaller 600 watt peak in Germany, the savings due to self-consumption of PV electricity are the only economic benefit. Let's now look at how we can use these values to evaluate the profitability of a PV system. One way to do this is to calculate the payback period, or PBP, after which the capital invested is recovered. The payback period is obtained by dividing the investment cost minus investment subsidies by the annual surplus, that is, the difference between the annual benefits and expenses. Since we do not take into account the time course of your income and expenses, but calculate with average values, this is a static calculation of the payback period. On the following slides, we'll take a look at the variables that influence the payback period and the amount it takes for an example plant. For this purpose, we consider a system in Cologne with a size of 10 kilowatt peak. We calculate with a system price of 1,200 euro per kilowatt peak. The investment costs of the plants are therefore 12,000 euro. We assume the annual operating costs to be 1.5% of the investment costs, so they are 180 euro per year. In order to calculate the annual benefits, we first have to calculate the yield of the plant. As we have already seen, the system yield is strongly dependent on the location of the system. For a plant in Cologne with an ideal energy yield of 1,100 kWh per kilowatt peak and a performance ratio of 0.8, the plant yield is 8,800 kWh. Let us first assume that all the electricity generated is fed into the grid. Until recently, the German feed-in tariff for the plant size of below 10 kilowatt peak considered here was 6.85 euro cent per kilowatt hour. This results in a profit of 603 euro per year. With the previously calculated values, the payback period is 28.4 years. This is a very high value, and it's due to the very low feed-in tariff. The background of the low feed-in tariff is to make self-consumption of solar power more attractive, which in turn leads to a release of the electricity grid. So for comparison, let's look at a plant where some of the electricity generated is self-consumed. For this calculation, we assume that the self-consumption rate is 30%. This means that 70% of the generated electricity is fed into the grid and 30% is self-consumed. The benefits are made up of the feed-in tariff and the savings from self-consumption. With 70% feed-in and a plant yield of 8,800 kilowatt hours per year, this results in a feed-in earnings of 422 per year. For the savings from self-consumption, we assume for simplicity that electricity prices will not change in the future. We therefore apply the current German electricity price of 32 euro cent per kilowatt hour. For the savings from self-consumption, this results in a benefit of 845 euro per year. The self-consumption of 30% of the generated electricity alone provides more benefit as can be achieved by the feed-in payments with full feed-in. In total, the benefits of this plant concept amounts to 1,267 euro per year. In this case, the payback time for the same plant is 11 years. This means that the system is paid off more than twice as quickly than a system with full feed-in. The economic efficiency of a plant in Germany can therefore be significantly increased by self-consumption of the electricity generated. In the next teaching unit, we will therefore take a closer look at the topic of self-consumption. But before we come to the end of this unit, I would like to come back to the consideration of full feed-in. For many systems, self-consumption of solar power is not easily possible. One example is a multi-family house or a tenant house where the system operator and the electricity consumers are legally different persons. In order to stimulate the expansion of photovoltaics in Germany, the feed-in tariff was therefore doubled in 2022 for systems that only feed electricity into the grid. For the plant considered here, this means a feed-in tariff of 13.7 instead of 6.85 euro cent per kilowatt hour. This increases the income to 1,206 euro per year, which is almost as much as for a plant with 30% self-consumption. Let's summarize this teaching unit. The payback period of a plant is the time after which the invested capital has been re-earned. Besides the investment costs, the main factor influencing the payback period are the annual benefits. These depend on the location of the plant, the local feed-in tariff, as well as the electricity price in case of self-consumption. In Germany, the electricity price is significantly higher than the feed-in tariff, so that the self-consumption of solar electricity almost always is economically reasonable. I thank you for your attention.